So now we're going to talk about what are often called human artifacts in experiments, which are kind of the consequences of real world people and how real world people, as well as ethical issues, can change experiments. And we're also going to talk about some more advanced analysis issues about how to analyze randomized experiments. Perhaps one of the most famous human artifacts in experiments, and actually it's not just in randomized experiments, not just in experiments, but in many kinds of research, it's known as the Hawthorne effect. And it's research subjects' reaction to being observed and studied. So that when you're being studied or observed, even if it's an observational study, never mind an experiment, people are like, ooh, I might do something differently now. So take a moment to think about what kind of experiments you think the Hawthorne effect would be large in. One reaction, or not reaction, but one way of dealing with the Hawthorne effect and trying to make it smaller is using unobtrusive or non-reactive measures, things that occur naturally or routinely or otherwise do not disturb subjects. So imagine doing an educational intervention, and in one version you have your own original data collection. You ask the students who are research subjects to fill out surveys or perform on a test that's just for your study. Compare that to one where you use as outcomes the ordinary exams and assignments and assessments that are done anyway in the course or the setting. Those are unobtrusive or non-reactive measures. They're naturally occurring. Researchers also will often ask the subjects if they can match the subject's administrative data, Social Security records, Department of Labor records, things like that that are collected, and if the subjects give their permission, the researchers can use those outcomes. Now, the Hawthorne effect has to occur a little bit anytime people know they are in research, and for the kind of research people like me do, and in university settings, biomedical, you have to ethically get people's permission and informed consent. But nowadays, of course, we're all experimented on by private companies who don't publish it and aren't doing research in the sense of generalizable knowledge that they'll publish. They're using it internally. And they do this stuff all the time. And if we just go to their website, right? So that's different than you agreeing to those long things that we never read, that Facebook and so on send. This is just, hey, I'm shopping, I'm going to someone's website. They're actually performing experiments on us all the time. They call them A/B studies, capital A / capital B. And, they're like, oh, what if we, design the website with blue versus designing the website with red? And we kind of don't know that they're experimenting on us. Maybe the stakes aren't so high. Stakes are kind of higher on social media, though, especially for political things and so on. Okay, so another kind of human artifact is what is known as the placebo effect, which I'm sure you all heard of even without reading the chapter. And that's the idea that people often respond to any kind of treatment, even a completely phony one, a useless one, right? That's the old sugar pill in medicine, or even more often, saline solution or things like that. And so because if people think they're getting something, there's some kind of psychological effect, which can be valuable in and of itself. they want to isolate the effect of some new drug or some new educational program or so on. So the ideal is blind experiments where participants don't know which group they're in, the treatment or control, I should say, or control. And that, reduces the placebo effect because both groups, think they might be getting something. But for some social experiments, that's impossible. Like, do you know whether you had job training or not? Yeah, you do know whether you had job training or no job training. Do you know whether you had counseling or not? Yeah, you know. Now, sometimes they try and reduce that by you get job training or you get some other kind of training or thing or event that you go to reduce it. But you can't blind people the same way in social experiments. Another thing people try to do is what is known in medicine as the double-blind experiment. So you're blinding the patients who are research subjects to which treatment they get. Also blind the researchers. So, hey, maybe you're really one of the innovators of this technique and you want it to work. But if you're measuring some medical outcomes for the research subjects, let's make you not know whether they are in the treatment group or control group, and that it won't influence you evaluating them. So obviously the big example you're hearing about right now are the developments of the coronavirus vaccines. And they take the double blindness so seriously that, in some cases, when they've had an adverse effect from a participant, something bad happened and they don't know if it's due to the vaccine. In some cases, they found out, that was actually someone in the control group, but I understand in some studies, they're not even finding out. No one's going to know, is that a control or someone getting the vaccine or someone getting some saline solution? It guards against biased observation. So what about in social and policy experiments and the kind of things we're interested in? Well, even sometimes when it's not possible to blind the research subjects, it is often possible to blind the research workers. So imagine that you're doing an educational intervention and you want to evaluate people's knowledge or skills. You can have the people measuring their knowledge or skills not know whether they're in the treatment or control, even if the subjects do, because I kind of know if I went to job training or not. So that's a way that you can guard against observation. It's also a way that the term double blind is not perfect for social experiments, because you kind of can blind the researchers in some circumstances, even if you can't blind the research subjects. Other human artifacts that are important are things like contamination, demoralization, rivalry. Contamination, we talked in the last video about leakage, where, the control group gains access or exposure to the treatment intentionally or unintentionally. And as we said, you can reduce that through cluster randomization design. Another thing is demoralization. Like, hey, they got the treatment, I didn't, There's this useful thing which can help me to get a job or help me get a better place to live. Think about the moving to opportunity one. And I didn't get it. And I'm neglected, I'm left out, I'm not working on it. What about rivalry? So the control group may feel like, oh, well, you got that, I'll show you, I can manage even without that. So obviously all this stuff depends on the population, it depends on the circumstances, the type of treatment, and so on. But it's all people reacting to knowing that they're in an experiment and looking at the other group. So some very important human artifacts are noncompliance and attrition. So noncompliance is when the treatment group fails to fully comply with the treatment. Like, I don't like this treatment. I'm not doing it. Again, this language comes from medicine, and I actually find it a little condescending. So think about it in the context of the Moving to Opportunity study, where they wanted to learn the effect of moving to a lower poverty neighborhood from people who were coming from high poverty neighborhoods. And obviously you can't just make that happen. You can't force people, you can't force society. So instead they gave these vouchers that only worked in low poverty neighborhoods. You can think of that as the effect of giving people the vouchers, and they may move, they may not move. We'll come back to that issue. But if your interest is in moving, then you'd refer to the families that actually moved to a low poverty neighborhood as compliers, and the people who didn't as non-compliers. So they're non-compliant because they didn't find any low poverty place that took their vouchers except that weren't very far away from the family that they wanted to stay near. So I don't think this is the greatest terminology, but it's the one that's standard. And it does mean you assign people to a treatment group and you say, hey, you guys are supposed to, follow this program, do the treatment. And some of them are like, yeah, no, I don't think so. I know I agreed to be in this experiment. You can keep collecting data on me, but yeah, I'm not doing that. Sorry. And that's a big one. There's also attrition, people just dropping out of the experiment. They get sick of answering questions. They don't have time for this, whatever. So, or they're just, the researchers lose track of them when they move. They try and develop ways not to, but they do. So you want to think about, attrition. If it's random, it's not a problem. If it's the same in the treatment and control groups, also probably not a problem. But what if it's different? And what if it's a consequence of the treatment? What does that do to your apples to apples comparison? So now we're going to turn back to results. So this is what we had before, looking at the results and how you calculate the effect of a treatment. And I had two examples, a quantitative variable like income and a categorical dummy binary or dichotomous variable like employment. And again, it's simple subtraction that you're looking for. So what's the big picture of interpreting results of causal studies? I want to sort of go over the whole thing. So first you start with the statistical significance. So if this was really a results table, there'd be something like a star here saying the differences were statistically significant. There might be standard errors or confidence intervals that you could judge and see non-overlapping confidence intervals to show statistically significant differences. So obviously that's like fundamental. If you don't have statistically significant results, you're not sure whether the program made a difference. Or if you have narrow confidence intervals, maybe you're sure it didn't make a difference, right? So statistical significance is important, but you don't want to just say, oh, not statistically significant, no, no effect. No. Maybe we're sure there's no effect because there's no difference with narrow confidence intervals. Maybe we don't have a statistically significant result and we just can't tell. But if we're going to conclude there's a result, we definitely start with statistical significance. Then, as I said before, we go to practical significance. Okay, so assuming this estimate is really true, what does it mean? How do we assess that magnitude? So we, gave some examples of that. We'll be seeing a lot more in the studies we look at. The third thing in a causal study is the quality of the causal evidence, also known as the internal validity, right? Within the study, how much do you believe the causal evidence? And again, this validity is different than all the measurement validity terms that we've had before. This validity, internal validity, is only relevant for causal studies, and it's about how good the causal evidence is, not is there a causal effect or not. But whatever you find, including zero, including no effect, how much do you believe that answer? Well, as we've been emphasizing, for randomized experiments, we believe it a lot. A lot. Yeah, we have to worry about biased attrition. We have to worry about some contamination, a few things that can ruin it, but for the most part, a randomized experiment has the highest possible internal validity, meaning when we estimate a causal effect, we believe it. If it's big, we believe it. If it's small, we believe it. If it's zero, we believe there's no effect. Of course, all of that's subject to the precision related to this statistical significance. Remember, when we had the observational studies, we did not have high internal validity. If we did a lot of work with theory and design and various analysis, we're like, this is our estimated effect. We've dealt with all these potential sources of bias, but we're still concerned about all these other sources of bias. So observational studies have much lower internal validity. And finally, generalizability, external validity. And again, we talked before about how to, in the second video, about how to assess the generalizability of a study. First, you look at how representatives your study subjects are from the population you're studying. Then you think about, hey, to what extent would these results apply in some other population, some other time, place, setting, context, and so on. So again, that's the big picture of everything you're going to do when you interpret the result of a causal study. So now let's go back to some of the narrower kinds of more technical aspects of analyzing it for estimating the estimated effect. So remember, what we showed so far was basic arithmetic. You got an average of the treatment group, you got the average in the control group, and you subtract. Well, what about fancier things like control variables that were so important in the observational studies? Well, it turns out that for the most part, because of the design of randomized experiment, you do not need control variables. You don't need to do that. The whole point of the design is to get balance. In some rare cases, it does make sense to have control variables where by chance the arms of the experiment are not statistically equivalent, not balanced. A very common example of that is if you're interested in an outcome like medical care costs that tend to be very skewed. Random things that affect whether someone is very, very expensive, only somewhat expensive, a patient, aren't going to be balanced. You're not going to have enough subjects to get that kind of balance. And so then the control variables, such as detailed medical conditions, might be used to make those two arms equivalent. So you will see control variables sometimes used when analyzing randomized experiments. Another thing that comes, actually this is more the design of the randomized experiment, but it's a more technical thing, is the issue of sample size and minimal detectable effects. So like when we're talking about, oh, I want to do a survey, how many people do I need to sample? Or like, oh, I want to do an experiment, how many research subjects do I need? How many do you need in each of them? Well, each group needs to be large enough to achieve balance, right? So they must be large enough so that you don't have by random chance these differences that are practically significant. And they also have to be large enough to get the desired precision of the treatment effect, right? You know, you're going to have an error in your estimated treatment effect, as for everything, confidence interval standard errors. You know, if you need your results to be very, very precise, you're going to need more research subjects. One thing you don't need that confuses students is you don't need the groups to be the same size. Students are often very concerned of like, oh, look, the control group, it's 3 times as large as the treatment group, then you can't make a comparison. No, that's wrong. Remember, you're comparing averages, like means or proportions. So, you know, you've taken into account the sample size. You need each group, each arm of the experiment to be big enough to get precision, big enough to get balance, but you know, you can get some of your added precision of your treatment effect maybe by having a really large control group, much larger than your treatment group, if, for example, the treatment is really expensive to administer. So what do people do before doing an experiment to figure out how big a study they need to have? So this is a more technical thing we're not going to go into in advance. You can learn a little more in Chapter 9, and that can point you to some more advanced things. But I think an important thing to understand is that there is a relationship between how many subjects you have, your minimal detectable effect, meaning, you know, how big a difference can we spot between the treatment and the control group? How big an effect of our program would be able to detect, and statistical power. Those 3 things are all related to each other. And so often, if you're commissioning a study or thinking about studies, it's good to think about what's the smallest detectable effect. Maybe you can only afford 200 subjects, and with that, the smallest detectable effect would be like incredible and amazing and really unlikely. You need to find a way to get more subjects. Or if you have the subjects you have, find out, oh wait, what are we going to be able to detect? Another thing to think about in analysis are heterogeneous treatment effects, meaning different people respond differently to treatments. Randomized experiments estimate an average of the treatment among everyone who participates, an average treatment effect among everyone who participates. You know, so all the people who are in the experiment, what difference does the vouchers make to no vouchers? But, you know, not everyone responds identically to an effect. You know, in effect, you know that there's no way they do. But as a practical matter, are there big differences between groups, big enough that matter? Well, there's 2 kinds of differences. One is differences between measured variables, from things you know about people. Oh, do men and women respond differently? You know, you can think about that. And moving to opportunity, do people who've lived in a neighborhood for generations respond differently to people who've been in their earlier, you know, their older high poverty neighborhood recently? If you have measures of those things, you can stratify your data, right? do an estimate separately for men and women, for longtime residents, newer residents of the old neighborhood. There are a couple of big buts about that. Be careful of data mining. Best to pre-register. There are also design things that you can do to plan. If you're stratifying, you can actually stratify before you randomly design. You can block things. So that's something you can put into design. For unmeasured variables, obviously you can't. You may think, oh, gee, people with particular personalities will respond differently. Well, unless you have some great personality tests that you were able to do at baseline, you think there's heterogeneous treatment effects, but you will not be able to estimate them. The last advanced analysis thing I want to talk about relates to that quote-unquote compliance. And this is known as a comparison between an intent to treat analysis or treatment on the treated or treatment of the treated. So here the point is that there are compliers and not compliers. Hey, you offered the vouchers to everyone and some people moved and some people didn't move. So the thing is, it's not random who made use of the vouchers and who didn't move, right? The whole point of the randomized experiment was to get rid of the self-selection between the people who moved to a not poor neighborhood and the ones who stayed in the poor neighborhood. Now we've changed that because we gave people vouchers, we made it financially more possible, but again, it's not random. So intent to treat analysis is comparing everyone in what they were randomized to everyone in the control group. That's the safest method because you know that's the one with your apples to apples comparison. And that's good. And to be honest, any randomized experiment should always do an intent to treat analysis. And in this case, it's a really useful thing. What was the effect of offering people housing vouchers that only worked in not poor neighborhoods? Very interesting, relevant policy thing. So again, intent to treat always should be done. But sometimes it's not giving people what they want to know. Like sometimes you're like, yeah, but I really want to know the effect of moving to the not poor neighborhood. That's what we want to know. And when we know it and say it turns out to be really big, well, maybe we can try and persuade people to use the vouchers. Okay, make the vouchers worth more money if we found out it's effective. So sometimes you really want treatment on the treated. Okay, now because it's not random who took up the treatment, you cannot estimate this without some assumptions. You simply cannot do it without some assumptions. So I'm going to show you the, I think, simplest and easiest to understand assumptions and a common way of doing this using the moving to opportunity example. So here's the moving to opportunity example. Here's the treatment group and here's the control group. The treatment group are the people that we offered the voucher that only worked in a low poverty neighborhood. The control group are the people who we made no such offer to, and we're neglecting the actual third arm they had with the vouchers that worked anywhere. We're just looking at these two now. Now, within the treatment group, there are what are called the compliers, the people who got the voucher, and they actually moved. There are also the quote-unquote non-compliers, the people you gave the voucher to, but they didn't move. Maybe they couldn't find a decent place without help. Maybe they couldn't find a place. Maybe they didn't want to leave their family, their schools, their friends, whatever. They didn't move. Okay? Now, because it's a randomized experiment, we know that the same subgroups exist within the control group. we know that there are a bunch of people who they didn't get the voucher, they were in the control group, but if they had been given the voucher, they would have moved. And we know that there are another group of people who, again, they didn't get the voucher, but if they had been given it, they would not have moved. And because it's a randomized experiment, even though we can't measure these characteristics, we know that these unmeasured characteristics, like would you have been a complier or would you have been a non-complier, are the same on average between the two groups. So far, so good, no assumptions. Now we're about to make some assumptions. This complier group in the treatment group, we're assuming that they are the only group affected by the experiment. We are assuming that these non-compliers, even though they said they'd participate and they gave the data and they got the vouchers and maybe they thought about using it, maybe they tried to use it, didn't work, they decided not to, we are assuming there is no effect of the experiment on them. And while I was just mocking that assumption, to first order for things like, finding jobs and stuff like that, being in the experiment is pretty small compared to actually moving to this quite different neighborhood. We are also assuming that the entire control group was not affected by the experiment. Oh, they got their hopes up. Maybe I'll get these vouchers. I'm giving all this data. They're reminding of this. No, again, we're assuming no effect. It turns out that if you do this, that you can get you can calculate the treatment on the treated effect just from knowing the intent to treat effect and the share compliers. Why is that? Well, that's because we know that the whole effect that we can estimate, the whole effect of the treatment group relative to the control group, that whole effect is due to the combination of the compliers and the non-compliers. But since we assumed the non-compliers, there was no effect on them, we know that the effect of the entire group is due to just the subset who are compliers. So it turns out in the moving to opportunity, about 50% of the treatment group, quote unquote, complied, meaning they moved to a low poverty neighborhood. And just to make up a number, because this is the wrong number, it wasn't anything like this, suppose that the intent to treat effect on earnings was $20,000, okay? And that was due to the half of the group that were compliers and the half the group that was not compliers. What that really means is that this group had a $40,000 increase in earnings, and this group had nothing. And the intent to treat for the whole is half or 50% of the 40K plus 50% times 0, nothing for them, to get an intent to treat for 20K. So I know that's a little more advanced, and don't worry if it takes you a while or you don't fully get it, but do be clear about the difference between the intent to treat effect on everyone and this thing about these compliers, the effect only on the people who take up the treatment. So now a lot of our discussion has sort of kept referring to the ethics of randomized experiments. Back in the first video when I introduced them, I said, oh, the evil, all-powerful researcher who just says, you're getting it, you're not. And as we talked about in causation, the fact that experiments are deliberately assigning treatment without people choosing which one. They can choose to be in the experiment, but if they stay in it, they don't choose which one they're getting. And without sensitivity to what would be best for them. So people have these, oh my God, experiments are evil. A lot of people have this, oh, that's not right. But in a lot of circumstances, it's totally ethical to do a randomized experiment. You may not know what works, and you're never going to find out in some circumstances without evidence like this. Randomization and lotteries, often used to implement them, can often be the fairest approach in a wide variety of settings. So Rachel Glenister is a development economist who's one of the people who is involved in the poverty lab that we talk about in the book. And, you know, she talks about in a lot of settings, people think that's a lot fairer than, the people who have powerful connections getting it. So randomization can be more ethical. And by the way, when we get to the next chapter, we're going to talk about a lot of circumstances that fall short of randomization, but are sort of close to it anyway. So going back to researcher obligations about how to do an ethical randomized experiment. So first, there's this principle called beneficence, meaning that there's no harm to subjects, but potential benefits. Secondly, there's this that you can't be like, oh, be in our experiment and it could hurt you. And there should also be like they get something out of it, some benefit, although it can be just feeling good about benefiting society. There's also justice. This is very controversial because it's sort of like, who do you experiment on? Are you being unjust in the broader world in terms of how you administer these experiments? So you'll see criticism of, for example, medical experiments, which can be done in poorer countries where it's just less costly to run the experiment. And people are like, oh, it's not fair. You're experimenting on poorer people with fewer options. So that's a live discussion in a medical context. You can also think about that in a wide variety of social and policy things. Another one is informed consent, that according to the traditional research ethics that evolved from biomedical research, people should participate in a voluntary way, and they should know that they're consenting. So if you think about social experiments, there's some where this is really important, like this might be a very high stakes setting for somebody. Do they get a job? They're great in a class, in an education thing. Where they live in the moving to opportunity. The stakes can be very high in real world settings for social and policy things. And the informed consent is very important, that people, know what they're doing and really agree to participate in that. And sometimes people can worry that people are kind of coerced into participating if the benefits are so large. Like, oh, the only way I get the chance of this valuable voucher is if I participate. And that's, again, discussions that people have. Again, I want to point out that a lot of online work done by for-profit companies these days either doesn't have any informed consent, or it's buried in the, thing it would take you 2 hours to read that we almost all agree on. It would take us 2 hours and we wouldn't understand very much of it. And yet, the social media companies and so on are in fact doing lots and lots of experiments on us all the time. What's the best algorithm to use for the feed that we see? And many people feel that this should be more highly regulated, that this, having all of us separately, like, click these things that we couldn't possibly understand, meaning we couldn't have informed consent, you know, is not fair and is not good, and that another system is needed for that. I'm not an expert on this, but I think a lot of people kind of feel that way. Oh, that I want to go back to the idea of informed consent, because it's not just so you agree, but you have to be able to understand what you're agreeing to. Of course, this can be very hard. You know, that's a big thing they worry about in medicine. You know, at what point does it get so complicated that you're like, I don't know what that means? But you need enough information to decide. Okay, and I talked about that randomization can often be the fairest in some settings. So what about qualitative methods? Randomized experiments are largely quantitative methods. You saw my numbers, my averages, and our estimated quantitative effect. And that's one of its strengths. But qualitative research also plays a large role in randomized experiments and some other kinds of experiments. First of all, at the design stage, as when you're doing a survey, but even more so, you really better know what you're doing before you design this experiment. You better know about the treatment, you better know about the population, you better know things about the treatment's mechanism, because if you don't know those kinds of things, you won't design the study well. You won't have the right version of the treatment in the setting. You won't have found a population where it would have an effect or that you'll see a difference. So exploratory qualitative research is very important beforehand, and it's especially important for both implementing the treatment and implementing the experiment. Are you going to get people who leave the experiment, who refuse to participate, all sorts of things. So qualitative research is very important to design. It can also be important for interpretation, both when the experiment is underway and you know, after you get your results. So while it's going on, you can use qualitative research to uncover contamination or other human artifacts in a field experiment. Both during and after implementation, qualitative methods can reveal possible mechanisms or processes. So, randomized experiment. Gold standard for evidence of causation, but a lot of limitations. Generalizability. You know, often you did it in one place in time and you don't know. It also doesn't get you inside the black box. That's why we were talking about using qualitative research for this. You know, not revealing how a treatment works. They're all the human artifacts. They're expensive. And most of all, they're simply unethical or impractical in many cases. One of my favorite examples is, you know, we really would like to know the effects of divorce on children and their long-term outcomes. How does it affect them psychologically, economically, socially, their own relationships? We'd really like to know that. Well, we will not be randomly assigning families to divorced and non-divorced status. And I like to say that because it's so clearly absurd, so clearly utterly unethical, utterly impractical, just bonkers. So there's tons of important things that we can't study with randomized experiments, but we still really, really want to know the causal effect. You'd like to be able to, if nothing else, tell families who are thinking of divorce, hey, you know, what will it do to the kids? Okay, so that's it. Finally, I know there was a lot of videos this time about randomized experiments. So next, we're going to turn to natural and quasi-experiments, which is really a kind of umbrella term for a lot of forms. And those are, if you want, somewhere in between randomized experiments and observational studies. See you then.